Welcome back to Solid State Physics class. Today let us discuss quantum theory of paramagnetism. You know the magnetic moment of an atom in free space mu is given by relation minus g mu b times j. Okay, so the magnetic moment is a vector quantity. Here g is called the Landé-G factor or spectroscopic splitting factor is given by 1 plus j into j plus 1 plus s into s plus 1 minus l into l plus 1 all divided by 2 times j into j plus 1. Okay, so this is the Landé-G factor. Okay, here j, s, l are the total angular momentum, spin and orbital quantum numbers. Okay, now and in this expression mu b is the Bohr magneton. Bohr magneton is given by E h cross divided by 2 times mass of electron. Okay. This value is 9.24 into 10 to the power minus 24 ampere meter square. Okay, and J is the total angular momentum. For electrons, G is equal to 2. If the atoms are placed in a magnetic field, then the potential energy U is equal to minus mu dot B. Okay, this is given by G mu B P into Mj, where Mj has values from J to minus J, J minus 1, J minus 2 up to minus J. Now let us consider the case of a single electron system. For a single electron, for example S electron, okay, 1s electron. So in this case, spin quantum number is equal to half and orbital quantum number L is equal to 0. Therefore J is equal to total angular momentum quantum number L plus S is equal to L plus S to L minus S. So L plus S is 1 by 2. Okay. Therefore we can write this thing Mj can have value from J to minus J. So J is 1 by 2 and J minus 1 is minus 1 by 2 up to minus J. So this is the values, these are the values of Mj if J is equal to half. For a single electron, Mj equal to half or minus half. Therefore the potential energy U is equal to minus mu dot B. Here minus mu for Mj equal to half, mu is equal to minus Mj is equal to half, mu is equal to minus G mu B into half. G is equal to 2, therefore minus mu B. Okay, therefore the potential energy is equal to minus of minus is plus mu B into B. Okay, similarly for Mg is equal to minus half, this will be, this is for plus half, and mu is equal to plus mu B for Mj is equal to minus half. Therefore the potential energy can be written as plus or minus mu B B for Mj is equal to plus or minus 1 by 2. Energy split into 2 plus or minus mu B times B. Okay, so we can draw the energy level diagram. When B equal to 0, this is the energy level. When there is a magnetic field, then the energy level split into two. One is, this is minus mu b b, and this is plus mu b into b. Okay, so the energy difference between these two is 2 mu b times b. Okay, so this energy level corresponds to mj equal to plus half, and this is corresponding to mj is equal to minus half. Here the magnetic moment mu is equal to, here in this case the magnetic moment is minus mu b, and in this case it is plus mu b. Okay, so this is the energy level diagram. So when a magnetic field is applied to the atom, then the atoms are arranged in any of these two energy levels. Okay, so therefore we can write there are total n number of atoms per unit volume. Out of that, n1 is n1 number of atoms per unit volume is in the lower level, and n2 number of atoms per unit volume in the upper level. Okay, so n1 n2 are the number of atoms or number of electrons per unit volume in the lower and upper energy levels. Therefore, from Boltzmann distribution, we can write the probability of number of particles in the ground level, or the fraction of number of particles in the lower level, n1 by n is equal to e raised to minus e divided by kt divided by e raised to minus e divided by kt. Okay, so this is equal to e raised to plus mu b divided by kt divided by e raised to mu b divided by kt plus e raised to minus mu b divided by kt. Okay. So this is n1 divided by n. Similarly, n2 number of particles, fraction of number of particles in the upper level is now the total magnetization or magnetic moments per unit volume m is equal to magnetization m equal to, here in the lower level the magnetic moment is plus mu, and in the upper level it is minus mu. Okay, the magnetic moments are directed opposite in both the case. So therefore n1 mu minus n2 into mu is the total magnetization, where n1 n2 are the number of particles per unit volume in each case. Okay, so therefore n1 minus n2 times mu. From the above expression into mu. Okay, therefore you can write this thing as n times mu into e raised to x minus e raised to minus x divided by e raised to x plus e raised to minus x. So this can be written as tan h mu b divided by kt. Therefore, at equilibrium temperature T, there are n1 number of particles per unit volume in the lower level and n2 number of particles per unit volume in the upper level. So therefore the effective magnetization or the net magnetization is equal to n1 minus n2 into mu. So from the Boltzmann distribution, you can write this thing as like this. Therefore the total magnetization is equal to n mu times tan h mu b divided by kt for single electron. Okay. At a high temperature, or when the magnetic field is weak, then mu b divided by kt is very much less than 1. Okay. In this case, the magnetization M can be written as M is equal to N mu times mu b divided by kt. That is, when x is very small, tan h x become x. Okay, so therefore M is equal to N mu times mu b divided by kt. So this is the magnetization. So from that we can get the susceptibility. Okay. Now, in general, an atom with a total angular momentum J in a magnetic field B, in a field B, atoms with a angular momentum quantum number J has, there are 2J plus 1 equally spaced energy levels. Okay, so for a single electron system, there are only two energy levels corresponding to mj is equal to half and mj is equal to minus half. But here, for more than one electron system, J is the total angular quantum number. Then there are 2J plus 1 equally spaced energy levels. Okay, so when a magnetic field is applied, the energy level split into 2J plus 1, 2J plus 1 levels. Okay. In this case, the magnetic moment mu can be written as and the potential energy U equal to minus mu dot B or minus mu Z into B. Mu Z is mu cos theta. Okay, Z component of this field. Okay, here magnetic field is along the Z direction. Therefore, the net magnetic moment. This is the magnetic moment of one magnetic dipole or one atom. The net magnetization M is equal to, this is the total magnetic moment per unit volume. So n number of magnetic dipoles are there per unit volume, or n atoms are there per unit volume. Then this is equal to n times mu z, average mu z. So our aim is to find out the mean or average z component of magnetic moment. Okay. Using statistical mechanics, the single particle partition function Q1 is equal to partition function summation e raised to m x divided by j. Okay, where x is equal to g j into mu b divided by kt. Okay, therefore by expanding this thing we can write this thing as the first term is of minus j, and next term is minus j plus 1, the next term is minus j plus 2, etc. So therefore this can be written as e raised to minus x plus e raised to minus j plus 1 x divided by j, etc. e raised to j minus 1 x divided by j plus e raised to, the final term will be e raised to x. Okay, so this, so we can take e raised to minus x from all these terms. So therefore this first term will be 1 plus e raised to x by j, then e raised to 2x divided by j plus etc. The last term will be e raised to 2x. Okay, so therefore this can be written as e raised to minus x into, so the bracket term is a geometric progression of 2j plus 1 terms. The first term is 1 and the common ratio is e raised to x by j. So the sum of these terms is given by a into r raised to n minus 1 divided by r minus 1. Okay, so here there are 2j plus 1 terms, and the first term is a is 1 and r is e raised to x by j. Therefore this can be written as e raised to x by j whole raised to 2j plus 1 minus 1 divided by e raised to x by j minus 1. We can take e raised to x by 2j into 2j plus 1 from these two terms. So therefore we can write e raised to minus x e raised to 2j plus 1 x divided by 2j into e raised to 2j plus 1 x divided by 2j minus e raised to minus 2j plus 1 x divided by 2j. Similarly, we can take e raised to x by 2j from these two terms. So e raised to x by 2j into e raised to x by 2j minus e raised to minus x by 2j. So these all terms get cancelled. Okay. So this is nothing but sine h 2 sine h 2j plus 1 x divided by 2j divided by 2 sine h x by 2j. Okay, so this is the single particle partition function. Therefore the mean z component of magnetic moment of an atom is given by kt partial derivative of this log q1 with respect to the magnetic field. By doing this we'll get g mu b into j into 2j plus 1 divided by 2j into cot h 2j plus 1 x divided by 2j minus 1 by 2j cot h x by 2j. Okay, so this is the mean mu z. Therefore the net magnetization m is equal to n mu z, which is equal to ng mu b j into 2j plus 1 divided by 2j cot h 2j plus 1 by 2j into x minus 1 by 2j cot h x by 2j. Okay, this is called the Brillouin function pj of x. Okay, so therefore we can write the magnetization m is equal to ng mu b j into bj of x. When x is very small, cot hx can be written as 1 by x plus x divided by 3 minus x cubed divided by 45 plus etc. Okay, therefore by using this thing in this equation, when mu b when x is very small, in our expression we can write Pj of x is equal to x divided by 3 j plus 1 divided by j. Okay, now so if x is equal to is very much less than 1 here, if the field is very weak or at high temperature, this is very much less than 1. In this case we can write this thing as x divided by 3. Pj of x can be written as x divided by 3 j plus 1 divided by j. Okay, therefore the magnetization M is equal to n g mu b j bj of x. Bj of x is g j mu b p divided by kt divided by 3 x divided by 3 into j plus 1 divided by j. So this thing is n g square mu b square b into j into j plus 1 divided by 3 kt. So this is the net magnetization when x is very much less than 1 or at a high temperature or weak field. Magnetic field is weak. Therefore susceptibility chi is equal to mu 0 m by b. Okay, this is equal to mu 0 times m divided by b is, so this b get cancelled, n g square mu b square j into j plus 1 divided by 3 kt. Okay, so this is the susceptibility at high temperature. So therefore we can write this thing as chi is equal to, so c divided by t, a constant c divided by t. So this is inversely proportional to temperature. So the susceptibility is inversely proportional to temperature, where but this constant c is equal to mu 0 n g square mu b square j into j plus 1 divided by 3k. Okay, so this is called Curie constant. Curie constant, and this expression, this is called the Curie's law. So this is the quantum theory of paramagnetic susceptibility. So we have derived the magnetization for single electron atoms as well as atoms with more number of electrons.